The drag force and terminal speed. A fluid is anything that can flow, generally either a gas or liquid. When there is a relative velocity between a fluid and a body, either because the body moves through the fluid or because the fluid moves past the body, the body experiences a drag force D that opposes the relative motion and points in the direction in which the fluid flows relative to the body. Here we examine only cases in which air is the fluid. The body is blunt like a baseball rather than slender like a javelin, and the relative motion is fast enough so that the air becomes turbulent, breaks up into swirl behind the body. In such cases, the magnitude of the drag force D is related to the relative speed V by an experimentally determined drag coefficient C, according to D equal to half C rho A V squared, where rho is the air density matched with volume. A is effective cross-section area of the body, the area of a cross-section taken perpendicular to the velocity v. The drag coefficient C, typically value range from 0.4 to 1.0, is naturally a constant for a given body because if V varies significantly, the value of C can vary as well. Here we ignore such complications. When a blunt object falls from rest through air, D gradually increases from zero as the speed of the body increases. Going down, you have the drag force D, proportional to the V. Okay. As suggested in the figure, if the body falls far enough, D eventually equal to the body's weight, Fg, mg. And the net vertical force on the body is then zero. By Newton's second law, the acceleration must also be zero then. And so the body speed no longer increases. The body then falls at constant terminal speed, Vt, which we find by setting D equal to mg in above equation. Terminal speed Vt, Fg minus D equal to ma equal to 0. And this D is half C rho A Vt squared. Okay. So this way we found Vt. Vt equal to mg 2 over C rho A.
We all know that very light objects, such as this piece of paper, appear to fall slowly. But is the slow descent caused only by their light weight, or is there some other reason? If we crumble the piece of paper into a tight ball and drop it next to a flat piece of paper, the difference is clear. There is more air drag on the larger surface of the flat paper, slowing its descent.
We are used to seeing light objects fall more slowly than heavy objects. But why do light and heavy objects fall differently? We will use this pair of tubes containing metal and paper discs to show the effect of eliminating air resistance. This is how the objects fall when the tubes are filled with air. If we now remove most of the air from the tubes with a vacuum pump and repeat the demonstration, the results change dramatically.
Have you noticed that objects tend to move more slowly through a viscous liquid such as glycerin? We'll drop various balls into this tube of glycerin to see how quickly they sink to the bottom. For comparison, here is how a glass ball falls in air. Here is the same ball falling in a tube filled with glycerin. It falls much more slowly. Here is a heavier steel ball falling in glycerin. Here is a still heavier lead ball falling in glycerin. Here are all three balls falling side by side.
Sample. A raindrop with radius r 1.5 millimeter falls from the cloud that is at height h 1200 meters above the ground. The drag coefficient C for the drop is 0.60. Assuming that the drop is spherical throughout its fall, the density of the water, raw water, is thousands of kilograms per cubic meter, and the density of air, raw air, is 1.2 kilograms per cubic meter. Question A. What is the terminal speed? By formula chemistry, 2 mg over square c rose. We put the number inside. Okay. The m of the ball is volume and the rho. Okay, is water, and the volume of the sphere is 4 pi cubic r over 3. And the area, cross area, is pi r squared. C is 0.60. And the radius r, this r is 1.5 millimeter, is 1.5 times 10 to the minus meter. And the raw air is 1.2 pricks. And the raw water is thousands of kilograms per cubic meter. All these one we put in the formula. Okay, you get an answer. That's very straightforward. Okay, about 7.4 meter per second and 25 kilometer per hour. Question B. What would be the drop speed just before impact if there were no drag force? Then we know V equals square root 2gh. The h is 1200. Okay, so if without a drag force, it would be 153 meters per second, much larger.